Okay, good morning. So today we will continue for the last part related to the BJT, which is related to how in the end we can still derive some equation to calculate the current in the bipolar junction transistor. So first of all, we're starting from the minority carrier distribution. So as I mentioned here, we are interested in calculating the current in the bipolar transistor. And similar to the case of the PN junction, the current in the bipolar transistor are determined by the minority carrier. So that's why in the last lectures, we focus on the minority carrier distribution because in the end, we will use the minority carrier distribution to estimate the current in the bipolar transistor. So here is some of the notation that we will use later on for the current calculation. So first of all, we focus on the forward active mode. So as we already mentioned last time, the forward active mode, and in this case, the base emitter junction is forward biased, and the BC base collector junction is reverse biased. So since there are two N-type regions which are emitter and collector here, so we have the minority carrier holes in these two places. So we have a minority carrier holes in the emitter and collector. So that's why in the last time we have already drawn this minority carrier distribution in the emitter and collector, where the distribution is related to the minority holes. And in the base region, the steady state excess minority carrier electron concentration is found from the bipolar transport equation. So basically, we can use a similar equation where we derived before, and use that equation and consider in the case in the base region, which are as shown here. So in this equation, where NB is excess minority carrier electron concentration, and dB and also the the tau B0. This is a tau B0 as a lifetime. As a minority carrier diffusion coefficient and the lifetime in the base region. And also right now we consider under the forward active bias, we start to have the excess electron concentration in the base region, which can express as shown here. So therefore the general solution for this function is shown here, which is equal to the exponential plus another exponential, and where LB is a minority carrier diffusion length in the base. And therefore we have to consider several boundary conditions where at x equal to 0 and this will be equal to this case, and also in the x equal to xb, that's the end of the base region, which is here. So we have to consider the boundary condition at this region and also this region. So by consider these two boundary conditions, we can start to solve this equation, and we just put it here inside, and also with this term with another boundary condition. In the end we can have the coefficient A and coefficient B can be calculated, and therefore we have finally the equation that can express in the excess concentration in the base region. And similarly, we can also using the similar concept to calculate the excess hole concentration in the emitter region. So the same approach is similar to what we have been already shown, that we consider the general solution and put in as a boundary condition. In the end, we can solve this equation. Also, we're doing the similar things again in the collector. So basically, we are doing the very similar calculation in the base region, in the emitter region, in the collector region. So in the end, the most importantly, the conclusion is shown here. We have the excess concentration in the base, emitter, and collector region. That's the equations are shown here. If you really plot the curve based on equations, that would be exactly equal to the curve where we already draw last time. For example, we have the excess here, we have the carrier concentration NB, and also here and here. So the calculation for this equation is just give you some idea that how we in the end derive the current here, and the most important part is actually related to the current gap. And in the bipolar transistor, we have the current gain, that's a transistor current, and low frequency common base current gain. That is actually very important for us. And if you look at the same concept for the current gain in the MOSFET, so in the case of the MOSFET transistor, as we apply the gate voltage here, then after the once the voltage is larger than threshold voltage, we start to have the drain current here. And also in the MOSFET, we have the similar definition for the current gain, which is we call as a transconductance, which is by definition is our current, drain current, the correlation between the drain current versus our voltage, and where we consider the increase of the drain current versus the increase of the gate voltage. So that's why we put as a derivative of here. So that's the current gain in the case of the BJT. And also similar, we will be very interested in the current gain in the bipolar transistor. So the basic principle of operation of bipolar transistor is to control the collector current by the base emitter voltage here. So we actually control the collector current, which is collector currents here, by control the base emitter voltage. So this idea is very similar like in the case of MOSFET, right? So MOSFET, our operation is to control the drain current by modulating the gate to source voltage. So the operation or the operation goal for the MOSFET and then the bipolar junction transistor are very similar. So the collect current is a function of the number of majority carrier reaching the collector after being injected from emitter across the base emitter junction. So we define a common base current gain is a ratio of the collector current to the emitter current. So we have the collector current here, and after from the emitter side, we also have the emitter current here. So therefore, we are interested in the different ratio between the. We are interested in the ratio between the each current. We also have the base current here. So therefore, the first one we have here is a ratio between the collector current over the emitter current, and that's how we call this is alpha, which is a common base current gain. So this is equal to this collector over the emitter, and we call this as alpha. And another one we are interested in is the ratio between the collector over the base current here, and that's we call this as a beta, which is consider the ratio between these two. So in here we define the two current gain, and one is a current gain between the collector and emitter, and that's we call as a common base current gain. And another one is a ratio between the collector and the base current. That's a common emitter. Okay, and the next one is we will be interested in if we try to look at the details of how this contributing factor for this current gain. So then we have to go back again to look at the NPN junction to see that what kind of the contribution component that in the end to allow us to calculate for this current gain. So then we still use a similar schematic where we have been already drawn before, where we have these three regions, which are the NPN here. And also in here we consider this is our emitter, this is our base, and this is our collector. And for sure in each PN junction we have the space charge region in between. So that's a similar schematic we used before to describe how current can be flow inside the BJT component here. So right now we will also use a similar way to analyze the contributing factor for the current here. So the factor, the first one, we will start to have the factor of the JNE minus, which is the electron flux injected from emitter to the base region. And therefore this is our here. So as I mentioned here, that the first one we have the electron flux from the emitter into the base, and here we call as JNE plus here. And as the electrons start to diffuse across the base region, a few will recombine with the majority carrier's holes here. So now the majority carrier is holes in the P region that can have the recombination of this electron current here. And the majority carrier holes that are lost by recombination must be replenished from the base terminal, and therefore this replacement hole flux is called as a JRB plus here. And where is the JRB plus here is here. So first one we have this JNE plus here, and once it move in here we will start to have the certain recombination, and the recombination will have this direction here. So we will have this JRB plus show me here. And then the electron flux that reach to the collector is called the JNC minus here. So we will have the electron flux reach to the collector side. So we have a JNC minus here. And also the majority carrier holes from the base are injected back into the emitter, and in this case we will resolve as a whole flux called J plus PE. Where is this one? And some electron and holes are injected into the forward bias BE space charge region will recombine in this region, and this recombination will lead to the flux JR minus plus, which is this one. And also, we will have the generation of electron and holes that can occur in the reverse bias BC junction. And this generation yields a hole flux called JG plus here. That's here. And finally, the ideal reverse saturation current in the BC junction is denoted by the JPC0 minus, which is here. So in the end, we have all these components, the current components inside to contribute all of the current flow inside the bipolar junction transistor here. And to be honest, that for my experience, also when I was learning the semiconductor device, I think the BJT part is always the most difficult one because of it combines majority and minority the carriers here, and also when we consider the current contribution inside, it's difficult to imagine have the contribution factors in a drawing like in this way. But you have to get used. If you are really work on the bipolar junction transistor, you actually have to face this kind of analysis very often. Unfortunately, right now the BJT is only used in a certain very specialty technology. I would not say we didn't use. We actually still use the BJT very often, but not in the main technology, which will be mainly related to specialty, certain like the power device or certain like a high frequency HBT. We still use the BJT technology, and therefore, if you look at some of the professor when they lecture the semiconductor device, probably they will start to skip the part of the BJT because it's we don't use this very often like before, but still it's really important for the certain technologies here. And also I have a feeling that every time when we try to study the BJT, the most important is you need to have the patience. You need to really need to calm down and take the patience, try to read the text and think about this, because it's difficult to understand in the beginning. If you try to compare the BJT and the MOSFET, and in the end you'll realize that the MOSFET is really the easier one compared to the BJT. So this is only the advice I can try to give you. And there's nothing we can do try to simplify this, or nothing we can do try to make this easier for you to understand. Because if you look at the textbook, you look at every material, they all lecture in a similar way. and this is very like the knowledge that you need to have a patience to digest it. If you don't understand, it's fine. Just try your best to understand the goal, because the goal is not really to fully memorize this, because the goal is in the next slide, that in the end we want to have the equation to really understand what kind of contributing factor for our current gain. Okay, so here is just some of the summary that we have been shown. So we have the very similar profile that we have been drawn before, and this is all the detailed description for this the each current contributing factors. Okay, so as I say, in the end, the goal is trying to understand that what can be the contributing factors that can give us the way to estimate the current gain. So the first one we will be interested in is alpha, which we have made the definition is equal to the collector current over the emitter current. So now we have to understand that what kind of the factors contribute to the collector current and emitter current here. So we have the alpha, which is equal to the collector current versus the emitter current. So now we just have to understand that where is a collector current. So the collector current is here. As we already say, once we under the forward active, so you have the electrons flow from the emitter to base, and that's JNE. And once you reach the collector side, that's become the JNC. So then this is JNC here. But now, what would be the emitter current? So if you look at the emitter current, which will be this one. So we have this one is a contribution for the emitter current. This one is a contribution for the emitter current. We also have this one as well. So right now, it's very clearly that the emitter current is the combination of these three. So that's our purpose. So as I say, you might get confused when we describe all these contributions, but in the end, our goal is try to go to the details to understand that what kind of the current components in the end become the emitter. So we now realize that there will be the three current components. One is this one, and this one. So all these three will become the current in the emitter side. And now we can also start to play small tricks, small mathematical trick, try to divide by these equation into the small three factors, which are shown here. The first one is So now we play a small mathematical trick, try to divide this term into the three factors here. And why we can do this? Just a very simple mathematics, because if you try to calculate back of these three, this and this can be cancelled, and this can be cancelled. So in the end, still remains this one. This is still equal to this. So that's just a mathematical trick. So let's just say again how we can make this 1 become the 3, because this one and this one can be cancelled, right? So this one and this one can be cancelled. So in the end, just remains this one over this one. That's equal to this part. So that's why we can start to expand the 1 into the 3 factors here. Now we try to make the a spatial name for each one. So now we define this alpha is also equal to this term, and where the first one, gamma, is exactly equal to this one. So this is our gamma factor here, and we have a name called this as the emitter injection efficiency. And if you try to look back for the plot as shown here, actually the gamma is just to describe gamma is equal to JNE over JNE plus JPE. So in here we actually consider this is a JNE and this is a JPE. So we are actually consider that how much the JNE can be flow from the emitter to base over the overall current here, which is JNE plus JPE. So that's why we call this as a emitter injection efficiency, because we are curious that once you want the forward active, you have a certain electron can be flow into the base, and that's the JNE. We want to understand that what would be the percentage of the JNE over all of the emitter current. So that's why we call this as a emitter injection efficiency here. And the next one is this one. The alpha T, which is the JNC as shown here. JNC over JNE, which is the ratio between this one and this one. And therefore we call this as a base transport factor. So the reason that we call this alpha T is JNC over JNE, which is the ratio between this and this. So clearly, as already mentioned, we have an electron flow to the base region, that's we call the JNE. In the end, we have the electron current will reach to the collector, that's we call the JNC. And part of the electron will be recombined inside the base region. So therefore, we are curious that the ratio in the end reach the collector over the beginning from the emitter. So that's why we call this as a base transport factor here. And the last one is this one. So that's we call this as a recombination factor. Recombination factor. So in the end, recombination factor is a ratio between this plus this over this, all three together here. So we are just trying to have this is recombination factor. So our goal is try to evaluate what actually the recombinations can be happen. I should use another this one. So try to evaluate that what would be the recombination the status inside in the emitter. So that's we call this as a recombination factor here. So again, if you look back to the two slides before, you might get confused at why we have to really go into the detail to describe, to understand each contribution factors here. But now probably you can realize that our goal is trying to see that what kind of the current component in the end can influence our current gain. And furthermore, we can divide by 3 factors, and which factor has a certain physics meaning. For example, the first one, we are curious what will be the emitter injection. So we calculate the ratio between the electron current reaching the collector over the electron current starting from the emitter. And also the second one, we calculate the base transport factor, which is just this over this one, and that's a base transport factor. And the third one is we are we are curious about the recombinations. Therefore, we have these recombination factors here. Okay, I think it's for the rest of it, just a little bit more further about the equation calculation. So in here, we won't go for the detail. It's basically you just put all of the equation we have been known and put several boundary conditions. In the end, the most important is finally we can start to estimate the emitter injection efficiency factor by the different doping, different width. For example, this is a base width and this is emitter width. So now we can start to estimate what kind of the result come from this design parameter for semiconductor for BJT, and in the end will influence our gamma factor. And similarly, also for the base transport factor, you should just put all the equations we have been knowing. Then in the end, we can have these results as shown here. And also for the recombination factor here, this is our result. Then we will be also very curious about the correlation between the alpha and then the beta here. So we can use a very simple circuit network to analyze the correlation between the alpha and beta. So if you look at this schematic here, so we have the emitter current. This is our emitter current. So basically, emitter current is equal to the base current plus the collector current here. So therefore, your emitter current is equal to your base plus your collector current here. And therefore, you can have these equations if you just divide by collect current, and then you can have this one, and this one is exactly equal to this one. So finally, we can have this equation that allows us to switch between the beta and alpha. So if you guys have already followed the electronics in the undergraduate classes, I think this should be pretty familiar with you, because that's in the part when we learning the electronics 电子学 related to BJT. In the end, we won't talk about this probably. In the case of the electronics, probably we won't talk about this, but we definitely have been already learned this in the electronics here. So now this is summary of all the equation we have been already used. And right now, what would be the design strategy if we want to have the higher current gain? So we can start to from this equation. So we can know the first one important is to increase the emitter concentration, and the second one is to decrease the base width. So if you try to increase the emitter concentration, then actually that will be increase your current gain, and also decrease your XB, your base width. That can also in the end to increase the current gain. These are the from in here is difficult to tell in the first sense, because of the equation here is relatively complicated, but in the end, if you try to increase the emitter, you always the concentration of emitters, you always can have the higher current gain, or decrease your base width. So basically, you can see from here, if you decrease your base width, for sure you can increase your beta, or you increase this one, you can also increase the beta. So in the end, our goal is to have the way to tell us that what kind of a design strategy to increase the current gain. Okay, so now we move to some non-ideal effects also has to be considered in the BJT here. The first one is the base width modulation, and sometimes we call this as an early effect. And to be honest, these effects is very similar to the channel length modulation in the MOSFET. So if you still remember in the MOSFET, we also have the issue called the channel length modulation. So the mechanism is because the base width is a function of the base collector voltage. So as we know, in the forward active, the base collector is under reverse bias. So therefore, your depletion, the base width here is actually will be influenced by the base collector space charge region, the base collector depletion width here. And therefore, if you try to plot the graph like shown in here, if this is the place x to 0 here, now if you try to increase your BC reverse bias, and you can expect your in the beginning your depletion width might be here, but as larger as your BC reverse bias increase, then your depletion width is actually become larger and larger. So this is a BC space charge region increase. And therefore, as you know, in the forward active mode, we have already mentioned that first of all, we have the excess electron concentration at this region, and because this is a reverse bias, so it needs to be 0 at this region. So we have very higher concentration gradient here, and if we have the wider space charge region, that will create an even larger gradient. This is this one. So as the BC reverse bias voltage increase, the BC space charge region width increase, and in the end, our base width is reduced here. So a reduction in the base width will cause the gradient in the minority carrier concentration increase, which in turn cause an increase in the diffusion current. So just let me explain again. So once we increase our base collector voltage here, for sure this space charge region is increased, and once this space charge is increased, the base width is decreased, and the base width decrease can lead to the increase of this gradient. And once the gradient is increased, that means the diffusion current is increased. So the we will have the minority gradient, minority concentration gradient increase. And once you have the concentration gradient increase, and that will lead to the increase of the diffusion current here. So now if you try to recall that a similar effect in the MOSFET, we also have the channel length modulation. That's because we increase our drain bias, and that will create a larger depletion region between the drain and also the channel depletion region, and that also will create in the end our channel length. The effective channel length is reduced. Okay, so in the end, if you try to look at the typical collector current versus VCE, so in the end you will have very similar the case like in the MOSFET. In the MOSFET, we also have the phenomenon where you will have this kind of the channel length modulation because of your effective channel length is reduced. Right now, you also have very similar results in the BJT here. That we just call this as an early effect here. And then you can try to extrapolate the voltage here. That we call this as an early voltage. And the next non-ideal effect is what we call as a high injection, or sometimes we just call this as a high level injection. These are the two terms are exactly has the same meaning. When we try to derive the current equation, when we try to talk about the current transport, we always assume this is a low-level injection. That means that your excess minority carrier concentration will not exceed the background doping, will not exceed the background majority carrier concentration here. But however, there's a possibility that actually our minority carrier concentration is become larger. So once we increase our base emitter voltage, the injected minority carrier concentration might approach or even become larger than the majority carrier concentration here. So this is to describe in the case we have the BJT here. So we have an emitter, we have a base, we have the collector here. So we have the N, P, N here. And as you know, once we forward the BE junction, we start to have the electrons will flow from the N to the P region. And the amount of the electrons injected from emitter is determined by our VBE. So there's a chance that your injected electrons here will start to exceed the background doping in here. And in this case, that's we call this as a high level injection here. So if you look at this is a plot, this is a plot for P base region, where we have this is a background base doping, and right now our injected electron here is higher than our background doping here. So that's the case where we have the high level injection will be occur at this moment. And in this case, we have the assumption that's called quasi-charge neutrality here. So once we have the quasi-charge neutrality, and that means the majority carrier hole concentration in the p-base region at x equal to 0 will increase because of the excess holes. So that means this one, this is a solid line, is a low injection, but the dashed line is a high injection. So we have this additional part. This is a part that the injected electron is larger than the background doping. In this case, the background doping is Na, which is Nb as shown here. So that means our injected electron is larger than our majority concentration in the base, which is Nb as shown here. And therefore, because due to this quasi-charge neutralities here, we start to see the increase of the holes here. So the original hole concentration is here, but now because still have to maintain the charge neutrality, so the hole will be increased as well. This is because the quasi-charge neutrality here. So because in the end the system has to maintain the charge neutrality. So once you have a high level injection, you have additional electrons, but still the base region has to maintain the neutrality. So there's an increase of the hole as well. So now the doping inside the base is not like here, it's become like in this way. So this is a case of the high level injections here. And the issue for high level injection is mainly related to the decrease of the current gain. So the current gain is decreased. So that's still the main issues under the high level injection. And if you try to look at some more detailed description here, the first effect is we will see the reduction of the emitter injection efficiency. This is because this one is increased. So since the majority carrier hole concentration at x equal to 0 increase with a high injection, more holes are injected back into emitter because of forward bias B junction. So right now, at this part, we have the higher hole concentration, and this higher hole concentration will start to inject back into the emitter part, which is this one. So you have a higher hole concentration. So more holes are injecting back into the emitter because of a forward bias of the base emitter. And increase in hole injection cause an increase in the JP current. And increase the JP reduce the emitter injection efficiency. So as shown here. So this one, this increase is because due to the high level injection, and therefore this one is reduced. So once it's reduced, that's why we see the beta is reduced here. So that's why, again, why we have to understand the current contributing factors inside, because this can help us to analyze some additional effects here. For example, the high level injection. And if you look back to the IV curve for the IC versus VBE, and then the most important for the high level injection is because we reduce the current gain. So under the large VBE bias, we start to see the slope is changed here. It's become 2P, become like show me here. So that's why the current increase is become slower because of the high level injection effect. And next one we also have to consider is the current crowding effects here. And although we actually plot the BJT like in this way, where we have the NPN, which is NPN, we have emitter, we have base and collector. But in reality, for sure, the device is fabricated like in this way. So we have a collector, we have a base, we have the emitter. And then the problem is that the current flow, which will be crowded always in the edge. And then very few current is flow in the center, and that's we call as a current crowding effect. And the current crowding effect gives us additional the thermal issue, or also the resistance issues here. So in the end, we actually design our BJT by consider this one, and this is the top view. So you have to imagine that you will see this transistor from top to the bottom. So each one, this is emitter, this is base, and so then if you try to make the cross sections from left to the right, and that will become like in this way. So you have the collector here, you have the base, you have this small part is emitter. So you have emitter here is here, and the base is here, and you have a collector outside, which is here. So that's a reality layout design for our BJT here. And in this way, we can make sure the current can be uniform flowing to each emitter and reduce the current crowding effect. So this is a very often used layout design technique to minimize some of the non-ideal effects come from the transistor. And also, there will be some issue related to the breakdown voltage in the BJT as well. So inside the BJT, there are the two breakdown mechanisms to be considered in the bipolar transistor. The first one is we call as a punch through. And this is because of if we try to plot the schematic of the BJT here. So we have an emitter, we have a base, and collector here. And you all know in each PN junction, there's a depletion region. There's a space charge region here. And the issue is that once we increase the reverse bias of the BC junction, and actually the BC space charge region will increase, right? So you can start to foresee the reverse bias BC junction will lead to the increase of the space charge region. And also, it will possibly start to extend and reach to the BE junction. So it is possible for the BC depletion region penetrate completely through the base and reach the BE space charge region. And this phenomenon is we call as a punch through, which is this one. So that's possible to lead to the punch through. And as I say, the punch through effect is also already mentioned in the case of the MOSFET. So once you increase your drain bias here, so now we all know the depletion region in the drain junction and also the substrate can be extended, right? So this VD increase and this width also increase here, and therefore that's exactly the same phenomenon in the MOSFET. We also call the punch through. In fact, in every semiconductor device, as long as we have the increase certain bias, you extend the depletion region and reach to another junction. In all kinds of semiconductor device, we all call this as a punch through effect here. So the punch through effect for sure will start to lead to the breakdown or the very high current, because right now your electron in here can start to flow and reach to the drain side, and also here the electron in the emitter can start to flow and reach to the collector side here, and without any of the experience the traveling inside the base region here. So, and here is a sum of the further equation here, so you can estimate the punch through voltage. Show me here, this is NB, and also you can estimate this one. So that's the sum of the equation for your reference here. And also similarly, these things can be also understood by using the Venn diagram. So this is a Venn diagram of N, P, N here. And right now, if you try to increase the BE bias here, so now we increase the reverse BC bias. So we have the EF here. And because we increase the reverse bias, so now our EF is become like here. And we have this one. So this is our reverse bias of the BC junction here. So now the electrons can start to flow to the collector side. So these Venn diagrams are very similar to the case of MOSFET. If you still remember, if you go back to check the slide in the MOSFET, we also draw in the similar scenes in the region between the source, channel, drain side. So basically, everything should be very consistent, no matter what you think about from the point of the BJT or from the point of the MOSFET. Okay, so another non-ideal effect for the bipolar transistor is still we will have to consider lesser chance to have the avalanche breakdown. So we have been talking about the avalanche breakdown many times. The first time is in the PN junction, and the second time is the MOSFET. And since in the BJT, we also is a combination of the two PN junction, and for sure, they can also happen for the avalanche breakdown. But in our case, we have to consider the two kind of the breakdown. The first one, if you look at the schematic for the BJT, it's shown me here. We have the NPN, we have the emitter, we have the collector, we have a base here. The first one is what we call the BVCBO. It's a breakdown in the open emitter configuration. So that means this is a breakdown which between the base and collector, and that's we call this as a BVCBO. And another one is this one. So we have NPN here. We have an emitter, we have a collector, we have the base here. And now we have the breakdown in between the emitter and collector here. So that's we call this as a BVCEO. And if you look at the electrical result between these two, it's shown me here. So we have the collector current, and usually we have first, this is a BVCO. So that's because of an open base. And another one, we have this one. It's called an open emitter. And that's called the BVCBO. And the correlation between these two is shown me here. And last part is just a quick overview for the possible circuit model that's available for the BJT. The first one is the Ebers-Moll model, and that's the model which considered the large signal model. Is a 4 operation mode, can be all considered in the BJT. And the second one is the gamma pool model, and that's a physics model and also consider some non-ideal effects here. And the last one is a hybrid pi model here. And here just a quick showing the Ebers-Moll, because that's the one of the most often used until now. And then that's also is a more easy one to understand. So basically it just consider this is one of the classical model for the BJT bipolar transistor, and it just consider like the different diode junction and connected together. So if we have this schematic for the BJT here, so we can consider the circuit model like in this way. So still we have emitter, we have base, we have a collector. Just in each PN junction, we consider as a one diode in series with a one current source. Also here so we have the base current here, emitter current, and also the collector current here. We have the here. So therefore, each IF can be expressed. This is IF, this is IR. And then in the considering this model, we consider the IE plus IB plus IC is equal to 0. So that's just for your information. If you need it, probably you can look back. In here, we don't talk too much for this model unless in the future if this model is needed for your work, you can always come back to look at again. And then last part, just want to share that we have been talking a lot for the BJT, and although it is true right now, the BJT is not the mainstream technology we are using for the logic or even for the analog, but sometimes we still need this technology for the very specialty application that's why we consider this is a specialty technology. And right now we are mainly use BJT for the power device application or in the high frequency application. And here just want to show you one example, like how in the end the real research work in terms of related to the bipolar junction transistor. And the idea is that all these terms mentioned in this paper is already covered in our lecture. So you can see the title is high current gain. So now you can see that's why we put a lot of time to explain the current gain, because in the BJT world everyone is really paying attention to the current gain. So the title is high current gain silicon carbide NPN bipolar junction transistor. So you see the title of this research is very straightforward. And if you look at the abstract, the author report a common emitter current gain beta of 55 in the NPN epitaxy emitter 4H SiC bipolar junction transistor. So from the first sentence of this paper, you already realize that the goal in this paper is that the author using some interesting material that we call the silicon carbide here and reach a very high current gain beta. So again, this is also the term we have been already knowing from these lectures here. And there's some detail. The space between the P plus B base contact and the edge of emitter figure is critical in the end to obtain the high current gain. And also, let's report the VCEO and also the VCBO. So right, that's exactly the one we mentioned. So that's why in the textbook we also talk about the VCEO and also the VCBO here. So that's why that as you see now in the case of this paper, I think at least from the abstract you can completely understand what the abstract want to tell with any further issues. Also, we can go for some details here. Bipolar junction transistors are attractive candidate for the power switching device because of there's the absence of critical oxide. That means there's no gate oxide, and also the very good for the conductive modulation and also near offset voltage. So these are some background information why that still people feel very interested in the BJT, because first of all they don't have the oxide, because the oxide is one of the issues for the reliability. So ideally, if the device doesn't have oxide, that can show that this should be the very interesting, stable and reliable device. And of course, what we be interested in is always after the however. So after however, the BJT requires a substantial driving current. This equation is something we already mentioned in the class. The ratio between the base and collector is a beta, and will dissipate additional unstable power. So as you see here, we can the purpose is the BJT should have the good the beta here, and also one of the show me here is the current gap will be reduced. The key term here still current gap. So as I said, the purpose of this work is all related to the current gap, and the rest of part is a detail we will not go through. And next interesting is to mention the purpose of this work. It's always mentioned in this work, and this work is in this work is very simple term, but no doubt you can use your own thesis or your own paper writing, because I also use it in this work many times. So in this work, these guys try to fabricate thermal oxidation that to avoid the gate oxide in the MOSFET, and also in the end, the goal is to reach to the current gap, the highest report value at that time, which is 55, and also there's a recombination of implant-induced defect have the important effect on the current gap. And the reason why this is also part, this sentence is mentioned, because if you look at the conclusion, let's also have the sentence mention this one. So we already mentioned before that basically the introduction part and conclusion part should be very consistent. Whatever the key point you mention in the introduction, you should rephrase again to mention in the conclusion. And also the first sentence, this one is also already here. So this is not only the one paper have this academic writing style. We have been shown, at least from our in our class, I think we have shown like maybe 3 or 5 papers. They all have very consistent academic writing style, like just show me here. And then the last things want to show in here is that although we don't understand this device very well, we don't understand how to lay fabricate, we don't understand what will be the very attractive point using silicon carbide, but at least from this key figure, it should be familiar with you guys, because this is exactly the same one that we have been mentioned in the lectures in our class. So the people are preferred to plot in the current gap versus a different. In this case, the x-axis is different, the collector current. So you can see that they were reporting the current gap beta, and up to the certain value here, and beyond the certain value, there's a start to decrease. And the reason why it decreased, probably you already have the answer in your mind, because this decrease is mainly related to the high level injection. That's already we have mentioned. So again, the knowledge we learn from this textbook, although it's very old, because that's already, this textbook have already published more than 10 years, 20 years, but still some of the classical knowledge is still very useful. So if you are new guys into the BJT field, if you don't understand, you still have to go back to check the textbook, because in the textbook, this figure is well explained. Okay, so that's end of our BJT. So we will take a short break for 10 minutes. We'll come back in the 11:10. Yeah, so for the one who missed the class last time, if you want to check your midterm, I will email you and then we will find another time in this week. You can come to the certain location and look at your midterm result with the TA. OK， 没问题。我们将会宣布一些期末考的事情，可以等到你们。我今天报纸在 YouTube 上面，或者你们之后看这个video。OK。 Okay, so let's just save some time. Probably we can finish a class earlier today. So today will be the last class for this semester. So we won't have the class in the next week. But as I already mentioned in the mail, so if you have any questions related to the homework or also any kind of question, you can email to the TA earlier, and then they will come to the class in the next 10 a.m. on next in the 10 a.m. on next Monday in this classroom. So let's just talk about something more about related to final exam. So this is already announced in the early time. So we have the two exams. So the midterm is a closed book and the final exam is open book. And we have a homework and we have the attendance here. So first of all, the final exam will be arranged in the June 11th on 6:30 p.m. So that will be the same in this classroom, but you need to come 10 minutes earlier. So probably because we need to divide by the two group of students. So one in this classroom, one in the next classroom. And it's open book exam, so you can bring anything you want. But the advice is that the open book exam is sometimes not easier than the closed book, because the closed book is already provide all the equations, and usually all the equations become the hint for you to address the question. For sure, in the open book exam, we won't provide any equation, and then the range for the exams cover everything from the beginning till today's class till the BJT. For sure, after this slide, we will brief talk to the JFET, but we won't include the JFET in the final exam. So it's basically from the beginning until the BJT. And as usual, there will be the certain amount of question from homework and example question in the textbook. And at least the calculator is needed. For sure, you can use, as I say, it's open book, you can bring anything. You can use the Excel, but sometimes Excel will be much smaller than the calculator. So still advice is to bring your own calculator. And also, although the open book, you can bring everything, but the previous experience from students tell me that if you bring too many things, that will waste your time to find the answer. Some students, they bring the textbook, they print out all the slides like this way, and then you bring everything in the classroom, but in the final exam. But actually in the end, it won't help, because you waste too much time to try to find the equation you need, try to find the answer, try to look at the concept. Of course, you can use Google, but also if you just quickly Google it, I believe you will get many information. Sometimes information is too much, that won't help you. So you still need to be very familiar with the basic material. So basic calculation, basic concept. Because if you are completely blank for everything, you just bring all the material, that in the end you still will probably get a very difficult time in the final exam. Okay, so that's all for the final exam. So the last part, we just quickly overview for the JFET. So the JFET still is not the mainstream for the semiconductor, but still very useful in case of some very interesting technology. We are actually use the JFET a lot. So the JFET, the full name is a junction FET. So that's the full name for the JFET here. So the basic JFET is considered to have the PN junction, just pure PN junction. So usually the device have this schematic, And still very similar, we have the source and drain here. So that's a N plus, that's N plus. But right now we have the N substrate. So in typical MOSFET we have the P substrate, but right now we have the N substrate here. And in the gate region, we actually have the P plus. And so the idea is to, this is our gate, source, and drain here. So the idea is to use this PN junction to control the channel. So as you know, once we give the forward bias or PN junction, your depletion width is reduced. But now you give a reverse bias, you actually increase this depletion region. So we can use these ideas to turn on and turn off our transistor. So this is another schematic for the JFET, PN junction JFET. So as I mentioned, that we actually mainly use this PN junction. So we try to give the forward or reverse bias to increase or decrease our depletion region, in the end to control the electron flow in the channel. So in the case of PN JFET, we still have very similar characteristic like the MOSFET. So we have in the beginning, we have VGS equal to 0 volt, because right now the channel is already there, the substrate is N-type. So that means if you look at for the IDVG curve here, at the VG equal to 0 volt, the current is already there because this is N-type substrate. So what we need to do is to apply the negative bias until a certain moment we start to pinch off our channel here. And finally we can switch off our device. So our threshold voltage is below 0 volt. And this is already something we have mentioned. This is called the depletion mode, because we need to apply the negative gate bias to deplete our channel here. So again, you have VGS at equal to 0 volt, so you have very limited your depletion region, so your electron can flow from left to the right here. And once you start to apply the negative gate bias here, you start to extend your depletion region. Then the electron flow in between is limited. So now you can see your current start to decrease here. Your current decrease, that means your resistance is increased here. In the end, after a certain moment, your VGS is smaller than your threshold voltage. So now you completely pinch off the channel. So now we won't have any current anymore, right? So that's a VGS equal to minus V2. So in the end, the concept for operating this device is very simple. Just use the idea, use the advantage of this PN junction. Once we give the negative bias, that means we start to extend the depletion region. After the depletion region is wider enough, then your channel is pinch off. then we won't have the current. So similarly, if you try to increase the VDS here, then we still have the saturation region. So this is a VDS increase here. Then we still can clearly see this saturation region. And this saturation region is because of the reverse, this one, so that the theory behind is exactly same like its MOSFET. So we have the reverse bias in the drain side. So therefore, you will have a larger reverse bias because of your VDS increase. So then you extend your depletion region. So you have a further pinch off once your the VDS is increased. So that's the first type. We use a PN junction, this kind of concept, to control the channel. Another type we call as a MOSFET. In here, we are not actually using the PN junction. We actually use a Schottky barrier contact here. So as you already know, when we talk about the Schottky contact or Schottky diode, actually the surface between the metal and the junction, if that's a Schottky contact, we still can form the depletion region there. So the idea is still the same, and the schematic here is shown me here. So we have the source, drain, and right now, still this is N substrate, but we actually only have the piece of the metal. On top of this N-type substrate, and the most important is this needs to be Schottky junction. And as you know, Schottky junction is once we apply the bias, you reverse this Schottky junction. You will still have the formation of the depletion region. So you still have, because at the zero bias it's a certain depletion can be already formed. And once you increase the bias, then your depletion region is reduced. So one of the most famous example for this kind of the MOSFET operation, or for this kind of a Schottky gate contact in the transistor, is actually not in the silicon base. It's mainly in the 3-phi. So in the 3-phi, we have what we call the high electron mobility transistor. And usually we call this as the hand, kind of the semiconductor transistor that we call this is as a hand, and that's a full name, it's a high electron mobility transistor. And in this case, you can see This is a case between the aluminum gallium arsenide and in this case, because of due to the Venn diagram or a certain polarization or certain 3-5 materials property, we can start to see the formation of this is our conduction band. But right now in this place, the conduction band is below our Fermi energy. So that means this is a place full of electrons. And this electron is well confined in this small place and with very high electron density. So that's we call this as an electron gas. So the gas, it means that the amount of electron is huge. So that's we call as a gas. And because also the electrons is confined in this quantum well here. If you look at the coordinate, we have the x, y, z. This is z. This is x, y here. There's no, because these electrons are pretty confined in this dimension inside. So the distribution along the x is very limited. The distribution for the electron concentration is only distributed along the z and along the y and along the z, and therefore the 3-dimensional distribution now has become the 2-dimensional distribution. So that's why we call as a 2D electron gas, because right now all the electrons can be distributed along the y and z, because the x direction is confined due to the quantum well here. So in the end, we can have very high density, electron density in z and y direction. So that's why people call this as a high electron mobility transistor. And similarly, not only in the aluminum gallium arsenide, also in the case of the aluminum gallium nitride. Gallium nitride, basically in the lots of 3-5 materials, all possibly to have this high electron density in the certain interface. So in the gallium nitride, aluminum gallium nitride versus gallium nitride, we also have this very strong 2-deck. 2DG between the algan and GaN. This is because of Fermi energy here. Is above of a conduction band. And then if you still remember, when we talk about band diagram, there's a concept called the degenerate. So once your Fermi energy is above your conduction band, thus we call this as a degenerate semiconductor, because we consider that's extremely high doping. It's a semiconductor like the metal. So this is exactly similar to the degenerate, because right now our Fermi energy is above our conduction band. So that's a place where your semiconductor is not like semiconductor anymore. It's like the metal. It's a very the conductivity is very high, and then because we have very strong electron density here. And how we actually turn on or turn off the transistor is using the same concept like the MOSFET. So if you look at the full schematic here, so usually the 2 deck, we already have very strong electron. This is our 2D electron gas. So that means the electron can already flow from the source to the drain, even there's no gate bias. So that means in the beginning, this is IDVG, and here we already have the current. Now we have to worry about is how to turn off this transistor. This is at the VG 0 volt. So similarly, like the MOSFET we have been mentioned, this is exactly the case like the JFET. We just need to apply negative gate bias until a certain moment. Your threshold voltage is negative enough to have larger depletion width. This is our depletion width. So once we have a depletion region is larger enough, then your electrons cannot be flow anymore. So now you can start to turn off your transistor. So that's the case how a typical hand operation. So you can see the typical hand operation is very similar to the ideal case of the MOSFET. So we just need a Schottky metal on top of this transistor, and we apply negative gate bias. In the end, we can turn off this transistor. So therefore, the typical hand transistor is a depletion mode type of a transistor. Okay, so that's all. So this is all for the JFET. So we won't go other detail. I think this is knowledge is enough. If you are in the future need this the knowledge related to JFET, you can always come back to look at the details here. So